Hello and welcome, honor students. Today we will go through our virtual lesson on the study guide for the upcoming test on Thursday over chapter 15 and 16.1 and 16.2. So we covered quite a little bit of material in these sections. So this study guide is to help us focus on the main concepts that we talked about. So I put this link on Moodle last week, so you have the blank study guide. So I would suggest that you fill this in as you go through and work out the problems. Pause the video, work the problems, and then go back and look at this video at the solutions to each of those so that you can check them off and say, I understand that particular concept. So let's get started. Okay, so first off, number one, says differentiate between the solute and the solvent. So just remember, we had learned this one previously, but the solute is the lesser of the quantities. The solvent is what is going to do the dissolving. So solute is dissolved in the solvent. The dissolving medium is the solvent. And also remember that like dissolves like. So you're saying a polar substance will dissolve a polar substance, a nonpolar, a nonpolar. So that's real important right there. So number one is differentiating solute and solvent. Number two is the properties of water. Water has a dipole-dipole interaction. So just, you gotta go back and just remember the properties because of the shape, and there is just the basic shape. And we talk about the delta positive on this side, and on this side here, the delta negative. And that is because of the electronegativity of the oxygen. It's holding those electrons slightly closer than the hydrogen. That's why the hydrogen's one proton is giving it a partial plus charge. So because of this, as you line up a bunch of water molecules, you have that dipole moment, and that has these attractions that hold onto one another. That's a dipole-dipole interaction. But water has a special dipole interaction called a hydrogen bonding. If you remember, the hydrogen bonding has to have a hydrogen, that makes sense. But it only can occur between hydrogens bonded to oxygen, nitrogen, I'll put commas there, or a fluorine. And that creates a special bond that has extra pull and extra attraction, and it's called hydrogen bonding. And that makes up a lot of the reasons why water has the properties that it has. All right, so first off, under properties, let's look at surface tension. Right here, let's talk about that, surface tension. So molecules on the surface's attraction to one another tend to minimize the surface area. Strong due to the hydrogen bonding, and an inward force or pull that minimizes the surface area. And that is surface tension. Water has a high surface tension. That's why you could float a rubber band. You could float a paper clip. You could float different things on water. A bug can walk across water. You do a belly flop in a pool, that's why it hurts, is because of surface tension. All the attraction of the molecules on the surface tending to pull towards one another is minimizing the surface area. Now that can be disrupted and broken if surfactants are added, and we talked about a surfactant, and right here is that term. So an example of a surfactant is detergents. Soaps and detergents are examples of surfactants, and they reduce the surface tension and thus break the hold that the water molecules would have on each other. All right. That is surface tension. So water in the solid state, that's our next point to look at. So remember, most of the time when you talk about a solid, the density is higher than a liquid because the particles are more compacted, stronger attraction. But when you talk about water in the solid state, it has the unusual effect that it's less dense than the liquid state. And that is why ice floats. And that is important when you talk about life being able to sustain. And that is of huge significance in Arctic and in those areas where the water freezes completely, and yet life continues. And that's how people fish and organisms live. If it wasn't less dense, it would freeze from the bottom up, and then you'd have a solid block, and life wouldn't continue in those particular areas for organisms that live in the water. So that's another important property, and that is because of the hydrogen bonding. Let's move the sheet up a little bit here. Solvation. So let's look at number 3 here, solvation. It's a process by which positive and negative ions of an ionic solid become surrounded by the solvent molecules and pulled apart. So remember, we talked about this in some depth. If you had NaCl, we know that's a plus and a minus charge. And what happens is water, if you're talking about water, it surrounds it. And around this positive sodium, you get all the oxygens facing with that slight negative charge. And around the chloride here, you get the hydrogens facing it with that slight positive charge. And it surrounds it and it pulls it apart. That is solvation. Number 4. Hydrate. Here's a bunch of terms, so please make sure you understand the terms and be able to apply those terms as well as solving. And that's what we're going to do at the very end of this. There is a number of solving problems that we're going to look at together. So let's do some definitions and just filling in some basic definitions. First, a hydrate. A hydrate's a compound that contains water of hydration. Water is in the crystal structure. So when you talk about hydrate, barium hydroxide, and then you have octahydrate, or you have copper 2 sulfate pentahydrate. So those are real important. That means a hydrate has in its crystal structure, water is bonded in there. Next, we have an electrolyte. An electrolyte is a compound that conducts electric current when in an aqueous solution or it's in a molten state. When you talk about electrolytes, ionic compounds are electrolytes. And when you talk about an electrolyte and you talk about an ionic compound, it only conducts when it is dissolved in water or melted. If it's in its solid state, it is a non-conductor because there's no free electrons to move. So that is an electrolyte. Salts are electrolytes. If you had a non-electrolyte, it would be something like glucose in water. It's not going to conduct. So that's called a non-electrolyte. Anhydrous. Anhydrous right here, that is a substance that does not contain water in its chemical structure. So that's anhydrous. A lot of organic compounds are anhydrous. Efflorescence. We talked about this term and we had some bell work activities with these terms in it as well. So efflorescence means the substance has a high vapor pressure. And if it's open in the surroundings, it will lose the water of hydration from its crystal into the environment because its vapor pressure is higher than the atmospheric pressure around it, or the vapor pressure that's surrounding it. So if a substance is efflorescent, that means it will lose its water of hydration into the environment. hygroscopic. Right here, we're at hygroscopic. That's a substance that removes water from the surrounding air. So any substance that will remove moisture from the air is called hygroscopic. When you talk about deliquescent, a substance that is deliquescent will actually remove sufficient amount of water from the atmosphere around it that will actually become a solution. So that means it's very hygroscopic and it's called deliquescent. When you talk about damp X, you buy that in the store. A lot of times people put that in their closet. That is made up of substances that are deliquescent. So it removes a lot of moisture from the air and it becomes a solution. Actually, if you notice in the bag, it becomes a solution. Number 5, calculate the percent by mass of water in barium hydroxide octahydrate. All right, so remember how we do this. We calculate the total mass, including the water, and we divide that into the amount of water, the mass of it. So let's get our periodic table and look what we have here. So we have here, and I'm going to write this down, we have barium, we have 2 oxygen, and we have 2 hydrogen, and we have 8 water. So when we look at barium, we have 137.33. So we have 137.33. 2 times 16 is 32.00. Here we have 2.02. And we have 8 times water. And water is 16, 17, 18.02 times 8. So we have 144.16. And these are all grams. So if we want to get the percent of mass of the water in this hydrate, we go the mass of the water, which is 144.16 grams, divided by the total. So we have to add up everything. So we go 137.33 plus 32 plus 2.02 plus 144.16. And that equals 315.51 grams. And we're going to multiply that by 100. And that'll give us our percent. So let's do that. So we go 144.16 divided by 315.51. And then multiply that by 100. So we have 4 sig figs. So rounding to 4 significant figures, this percent by mass of water is 45.69%. So that is our percent of mass of the water in that crystal. All right. Number 6, suspension versus colloid. So a suspension is a heterogeneous mixture from which the particles will settle out when you leave it sit. So you could shake it up, but when you sit, it will settle out. So that could be, for example, dirt in water. It could be oil and water. It'll just form layers. So it is said to be 2 or more distinct phases. So one thing to remember, particle size of suspension is greater than 1,000 nanometers. This here should have been 1,000. So let's just cross that. This is 1,000 nanometers and can be filtered. So a suspension is much larger and you can filter it. So 1,000 nanometers. Please notate that little typo there. It's 1,000 nanometers or greater. Now, when we talk about a colloid is also a heterogeneous mixture containing particles that range in size from 1 nanometer to 1,000 nanometers. So they are smaller than a suspension. The particles are spread throughout, but the particles do not settle out and you can't filter them. So you cannot filter a colloid and they will not settle out. We'll talk about why they won't settle out here in a minute. So a colloid could be solid, liquids, or gases. Cream, whipped cream, that is a solid and a gas. So there's a lot of different things that we're sort of used to and we understand. But that is a colloid. The size is less than a suspension, but not as small as a solution. So we'll talk about that here in a second. So if you talk about a solution is said to be one phase. So if you talk about, I'm going to just come right down here. I'm going to write down solution. That is a homogeneous mixture. One phase throughout. Now the particles are less than or equal to 1 nanometer. So these numbers are pretty important to have a distinction of what they are. So remember, a suspension is 1,000 nanometers or more. A colloid is 1 nanometer up to 1,000 nanometers. And a solution is 1 nanometer or less. So a solution is a homogeneous mixture. It's not a heterogeneous. The other two, suspensions and colloids, are heterogeneous. A solution is only one phase. You can see no distinct layers. It's all in one phase. So number 7, homogeneous mixture is said to be one phase, also known as a solution. The solute is evenly distributed throughout. So same thing as I just wrote down here. Now let's look at number 8 here, Tyndall effect. The Tyndall effect is the scattering of visible light by colloidal particles and suspensions. Solutions do not exhibit Tyndall effect. Now, the other day I had a bell work assignment where you mix some salt and water, and a lot of students said they saw the Tyndall effect in that. What you saw floating around in there is a lot of times particles that are in the water, especially if you got tap water, dust particles that were possibly in the cup. So there are a lot of reasons why you saw things when you shined the light through with the flashlight. But what you did not see is the actual beam, the highlight of the beam going through that salt water. You may have seen some things floating in it, but you did not see the actual outline of the beam. That's the Tyndall effect when you see that outline of the beam. And you can only see, please notate that, because a lot of students said they saw the Tyndall effect in a solution. You cannot see the Tyndall effect on a solution. It is only on a suspension or a colloid. And it's because these particles are being struck by the light and you can see distinctly the light coming through. So let me just draw two things here. So here you have a cup and here you have the light source. And you will see the light going, and it'll be bright if this is a solution. Let's say there's stuff in here. You're just going to see the light come through to the other side. You won't see a beam inside. But if you had this right here, and this was a colloid or a suspension, you will see the outline of the beam going through there. And that's the distinction between the Tyndall and non-Tyndall effect is you will see the beam itself, the outline of the beam, and that is only in a colloid or a suspension. Please make notate of that. There was some confusion on that one. All right, the Brownian effect. This is the reason why a colloid doesn't settle down. So remember, you have in a solution, so if I have a beaker here and I have a solution and I have a colloid in there, remember, in this solvent, the molecules are constantly moving. So remember, the size is 1 nanometer up until about 1,000 nanometers. So you have these particles that are in here, and they are constantly being struck by the movement of the particles in the solvent, striking it and making them move. That's why they can't settle to the bottom, because they're small enough that they're going to be bounced and jostled around. So this is the reason that colloids do not settle out. The constant collision of colloidal particles with the moving molecules of the solvent. That's Brownian motion. Number 10, 3 factors that affect how quickly a solute dissolves. So remember, the solute goes into the solvent to dissolve. It has to be like and like, so that is important. So if you talk about shaking or stirring, that's called agitation. These 3 factors will allow something to dissolve more readily. So agitation increases how fast something dissolves. You're shaking it or stirring it. Temperature, for the most part, for most all solid solutes, as you increase the temperature, more of the solute will dissolve. So the higher the temperature, just think about why. There's more collisions, more opportunities for solvation to be split apart and to dissolve. So the higher the temperature, the more solute will dissolve for the most part. There's a few exceptions to that, but for the most part, it is the higher the temperature, the more it will dissolve faster. It will dissolve faster. Number 3, the particle size. So the finer the crystal particles, the quicker it'll dissolve. So that is a cube versus fine granules. Fine granules will dissolve much faster than a cube because it's a surface phenomenon. So if you have a cube, all the surface has to have contact and start to be split away rather than everything having contact at once. Number 11, what is solubility? Solubility is the amount of solute that dissolves in a given quantity of solvent at a specific temperature and pressure. That is solubility. How much solute will dissolve in a specific amount of solvent? And once again, you have to hold the temperature and pressure constant at whatever range it is that you're looking at. How is solubility expressed? Well, it's usually in grams per 100 grams of solvent. If you're talking about a gas, it's grams per liter. But normally you're talking about grams per 100 grams of solvent. When we talk about solubility, we are generally going to be looking at molarity for concentration, but just understanding solubility can be expressed in grams per 100 grams of solvent. Number 12, saturated solution. So please pay attention on this right here. These have some terms that distinguish them, and it's important to have an understanding. So saturated solution contains the maximum amount of solute for a specific temperature and pressure, contain the maximum amount of solute for that given range of temperature and pressure. You can identify saturated because on the bottom of the container, if you have a beaker, and this is, you're going to have some crystal solids on the bottom. identified by solid on the bottom. Remember, it is in a state of dynamic equilibrium. As some of the solute on the bottom dissolves, others will redeposit on the bottom. And that's important. That's a saturated solution. It can't hold more. So if you actually added more, it's just going to dissolve some and drop some to the bottom, and it's going to stay in that equal, that dynamic range where it is in a state of dynamic equilibrium. Now let's differentiate that. That was saturated, now unsaturated. Unsaturated contains less solute than it can hold. It has less solute than it can hold at that temperature and pressure. There is no solute on the bottom. So it is for example, a beaker like this, and you have this liquid, and there's nothing on the bottom. If you add a little more of the solute, it will dissolve. That's a real important clue. That tells you it's unsaturated. Now, supersaturated. Let's draw this right here. Once again, when you look at it, you cannot tell if it's unsaturated or supersaturated. Why? Because there is no solute on the bottom. However, if you drop a little more of the solute in this container, they call it a seed crystal, because if you drop more in, you get rapid and constant precipitation occurring. So a supersaturated contains more solute than it can theoretically hold at that particular temperature and pressure. It's identified if a little more solute is added, called a seed crystal, then a solid formation will occur. And that's what you're notating between these 1 and 2 right here. That's what you're notating. Hopefully you paid attention. That's a real important distinction that I made between them. Number 13, miscible and immiscible. Miscible means a substance that will dissolve in another in any amount. Water and alcohol are miscible. It doesn't matter, whatever the percent is, it will mix. That's called miscible. Immiscible will not dissolve. You're talking about oil and water are immiscible, so they will not dissolve. They'll form distinct layers. All right, now we come to Henry's law. What does Henry's law apply to? Henry's law is all about the solubility of a gas in a liquid. Please notate that it is directly proportional to the pressure of the gas above the liquid. And Henry's law of solubility, and we looked and we worked a little bit with that. Solubility 1, pressure 1 equals solubility 2, pressure 2. And the pressure can be in atmospheres or kilopascals. That's Henry's law. Number 15, how does the pressure, and these 15 and 16, please pay very good attention to this. How does the pressure above a liquid affect the solubility of a solid in a liquid? There is no effect. The pressure above a liquid, when you're trying to dissolve a solid solute, has no effect. Does the pressure above a liquid affect the solubility of a gas in a liquid? Yes, it is directly proportional. So the higher the pressure above the liquid, the more will dissolve in that liquid, the more gas will dissolve in that liquid. Think about a soda bottle. They pump a large amount of gas in it, and they put the lid on. And what happens is that massive amount of gas pressure forces the gas to dissolve into that liquid. So it is directly proportional, whereas pressure has no effect on the dissolving of a solid. It has a lot of effect on the dissolving of a gas in a liquid. Number 16. How does increased temperature of the solvent affect the solubility of a solid solute? For the most part, a solid solute The solubility will actually increase if you have higher temperature because there's more collisions, more opportunities for it to dissolve. However, when you talk about a gas, and that's this part right here, you talk about a gas, the higher the temperature, the less soluble. Because now you have the particles on that liquid, that solvent, moving rapidly and striking the gas particles that are in there and causing them to escape. So the cooler the liquid, the more soluble. So it's the opposite of a solid. So temperature has the opposite effect on a gas. The cooler the solvent, the more gas will dissolve. Number 17, concentration. Concentration is a measure of the amount of solute that is dissolved in a given amount of solvent. Once again, the measure of the amount of solute that is in a dissolved in a given amount of solvent. And what we're going to be talking about is moles of solute in liters of solution. And that equals the capital M, and that's molarity. Number 18, differentiate a dilute solution from a concentrated solution. So dilute is as it sounds. It has a small amount of solute, so it is got a low concentration. If you talk about concentrated, a concentrated solute, that has a large amount of solute in it, large amount of solute. So that is important when you're talking about types of solutions and their concentration. So you have dilute and you have concentrated. All right. Molarity, I just made that distinction on number 17, but molarity is a number of moles of solute dissolved in 1 liter of solution, and that's moles per liter. And we can do calculations, and we have been doing some calculations. You have that as your bell work today. The dilution formula, really important. We have molarity 1 times volume 1 equals molarity 2 times volume 2. And that we can use a highly concentrated to make a dilute solution. And we will have practice on that as well. Number 21, be able to work out any type of problem that is dealing with Henry's law, molarity, dilution. So we're going to look at some examples of those now. I would suggest on these, maybe try them, pause the video, see how you do, and then look at the solution and compare. Number 22, calculate the number of grams of NaCl in 2.5 liters of a 5 molar solution. All right, so let's look at what we're going to do. So we have 2.5 liters, it's already in liters. It's very important to remember this. Let me just back up just a hair. The volume, when you use dilution, volume can be in milliliters or in liters. When you talk about molarity, anything dealing with calculations of molarity, it must be in liters. Really important that we have that understanding. If that confuses you, just change everything to liters and then you're safe always. All right, so this is already in liters right here. It says 2.5 liters. So I'm going to go 2.5 liters over 1. So it says, I'm going to solve for my grams here of NaCl. So I have a 5 molar solutions. So that means I have 5.0 mole of NaCl in 1 liter. That's what that's telling me. And I want to go from moles to grams. So I know that 1 mole of NaCl is, and I got to get my calculator out here. So Na is 22.99 plus Cl is 35.45. So that's 58.44. So it's 58.44 58.44 grams of NaCl. So our liters cancel here, our moles cancel here, and now I'm in grams. So I can plug this in and calculate the grams. So I can go 2.5 times 5 times 58.44. And I can't have more than two significant figures. So 730 grams. So that is an extremely concentrated solution of NaCl. All right, number 23. What is the molarity of a solution that has 100 grams of KCl for a total of 250 milliliter solution? So in this 250 milliliter solution, you have 100 grams of KCl. So we know that molarity, so we're going to go over here. Moles divided by liters of solution. So I have 100 grams. So I have 100 grams of KCl. I'm going to go to moles right away. So 1 mole of KCl is, and I got to get my periodic table again. So I know Cl is 35.45 plus potassium is 3910. 74.55 grams. All right. And so I have now in moles, and I want, and it says 250, so I put 1 over 0.250 liters, and that will give me my concentration. So I'm going to go 100 divided by 74.55 divided by 0.250. So when I look at this here, my molarity, and I only can have one sig fig, is 5. So this is 5 molar KCl. And if what I just did there confuses you, don't let that confuse you. You could just simply have gone like this as well. Calculate your moles. So you could have gone 100 grams divided by 74.55. And that comes out to 1.3 something. And then just put that over your 250.25 liters, divide it, and then that gives you that. So just keeping it simple and going through stoic, 5 molar, you would have just a slight difference if you would have done it the other way, because you would have rounded a different spot than I did. So if you did 100 grams divided by 74.55, you're going to come up to 1.34. 1.34 divided by 0.250, and that's going to equal your 5. The same thing I had. If you, and it's the rounding that could cause a little bit of confusion on that, but don't let it. So 5. You have to stay with the sig figs though, that you can't change that. Number 22, the solubility of a gas in water at standard temperature is 0.26 grams per liter at 2 atmospheres. What will the solubility be if the pressure is increased to 6 atmospheres at standard temperature? So standard temperature for a gas is 0 degrees Celsius. You could be talking about 25 degrees because that is for solution. So you could say 25 degrees Celsius. All right, so this is Henry's law. So when I look at this, I know right away this is S1 over P1 equals S2 over P2. I'm going to write this out as S1 P2 equals S2 P1. So I'm going to come over here and write down S1 P1 S2 P2. So it says the solubility of the gas at standard temperature is, solubility is 0.26 grams per liter. Pressure is 2.0 atmospheres. It says, what will the solubility be? So this is blank grams per liter. And the pressure 2 is 6.5 atmospheres. All right, so I'm solving for S2. So I'm going to divide by P1 and get rid of it right here. So now I have S1. So I have 0.26 grams per liter. And I have P2. P2 is 6.5 atmospheres. And I'm going to divide that by P1. P1 is 2 atmospheres. Atmospheres cancels, and that leaves me in grams per liter, which is what I'm solving for. So let's solve this out real quick. 0.26 times 6.5 and divide that by 2. All right, so now I must have two significant figures. So it is 0.85. 0.85 grams per liter, and that is my answer. Does it make sense? Well, yes. At 2 atmospheres, my solubility is 0.26. So if I raise my pressure to 6.5 atmospheres, now my solubility is 0.85. So it went up, and they're directly proportional, so that makes sense. Number 23, solubility of a gas in water is 0.45 grams per liter at 101.6 kilopascals. Assume the temperature is held constant. What is the pressure when the solubility is 0.22 grams per liter? So my solubility fell. So that tells me immediately I'm looking for a lower pressure. So I will, once again, I sort these always the same. I write down everything. S1, P1 equals S2, P2. And I go S1, P2 equals S2, P1. Now I come over here and I write down all my variables. S1, P1, S2, P2. All right, so my solubility is 0.45 grams per liter. My pressure is 101.6 kPa. My solubility is 0.22 grams per liter. And my pressure is blank kPa. So I don't know what that one is. So that's what I'm solving for, is my pressure 2. So I'm going to divide by the solubility 1, and that will give me my pressure 2. So solubility 2. So solubility 2 is 0.22 grams per liter. And my pressure 1 is 101.6 kPa. And my solubility 1 is 0.45, and that's grams per liter. And grams per liter cancel off, leaving me in kilopascal. So now let's plug this in. 0.22 times 101.6 divided by 0.45. So I have two significant figures. So I have to round this. So I would say that, because it comes out to 49.67, and I have two significant figures, which means I should have it as 5.0 times 10 to the 1 kPa. So it would be 50 kilopascals But because I need two significant figures, 50 is only one. I could go 50 and a dot, but this is simpler to do. All right, so like, does it make sense? So at 101.6 kilopascals is 0.45. So I am dropping by over half my solubility. That should mean my pressure should go down by at least that, and that's what we see happen here. It's down to 50 kilopascals. Number 24. A lab member obtains 25 milliliter stock solution of 6 molar HCl, adds 75 milliliters of water to make a 100 milliliter sample. What is a new molarity or concentration of the solution? Hey, this is our dilution formula. So I have M1V1 equals M2V2. And I can use milliliters in this, not a big deal. So I get 25 milliliters of this highly concentrated HCl. So that's on this side right here. So I'm gonna go 6 molar, and then I have 25 milliliters. I'm looking for my secondary molarity, so I've got M2. And don't let this confuse you. They added 75 milliliters, but the ending volume is 100 milliliters. So be careful on some of the terminologies. So I'm going to divide both sides by 100 milliliters. Milliliters cancel off. So my secondary concentration, M2 equals, so let's plug this in, 6 times 5 divided by 100. So I need, well, I only have one sig fig. It comes out to 1.5 molar, but because I only have one significant figure here, I have to round that to 2. So this is a 2 molar HCl solution. I had to round it from 1.5 to 2 because we had one significant figure. So that is my new dilute solution. Number 25, calculate the moles and grams of solute in a 500 milliliter solution of 0.1 molar calcium chloride. So calculate the moles. All right, and grams. So we got two different things we're trying to do here. So we have a solution that is 500 milliliters. So that is 0.500 liters over 1. So let's do our moles first. So we have a 0.10 molar, so that means 0.10 moles of CaCl2 in 1 liter. So I can stop right there and calculate my moles. So I have 0.500 times 0.10, and I have 0.05 moles. It's 2 sig figs, so 0.050 moles of calcium chloride. So I calculated my moles already. But it also asks for grams, so I can go one more step. So 1 mole of CaCl2, and I got to get my calculator and my periodic table. So I have 35.45 times 2 plus calcium, and calcium is 40.08. 40.08. So I have 110.98 grams CaCl2. All right, so now I can get my grams and I solve this one. So 0.500 times 0.10 times 110.98. So once again, 2 significant figures. I have 5.5, 5.5, grams CaCl2. All right, so that is, ladies and gentlemen, how to solve both of the molarity, molarity to moles, and then to grams. So hopefully you followed this, saw a lot of work on here, a lot of different styles of problems. Your bell work today is some molarity. Tomorrow's will be some dilution, and then at that point you should be prepared for the test. So once again, this study guide took a little bit of time to go through. Please, hopefully you printed it and do take the time to go through all these notations and try and solve these problems. Pause the video, check your work, come back and see the solutions to them, and hopefully you got them. So please don't forget that Thursday is the test. You have 45 minutes and it has to be done by 3:05 p.m. So once again, thank you for watching this video. Go in peace. We'll see you soon.